So that's what we'll start with. So on, all right. What was that? A hiccup, a sneeze? Yeah, it is what it is. All right, so problem 1H. And this was, I believe, homework 4, yeah. So here's the integral in question. It's a beautiful integral, if you like scary looking creatures, and we all do. And so the way I would encourage you to think about this is to look, you know, one of the first things that you should come to your mind when you have radicals is, do you have sort of these difference of squares in them? And if so, that's a good sign, or a sum of squares inside. It's a good sign that using trig can be useful. And in particular, the 81 minus x squared is telling us to do the following. So the term 81 minus x squared suggests that we set x equal to 9 sine of some new variable, which I'll call theta. And if that is my x, then my differential, my dx d theta, can be expressed as 9 cosine theta d theta. All right, so here's the thing. We got to plug this in now. And you know, depending on how comfortable you feel with this can either make it look much uglier or much cleaner right away. It just depends on, you know, every one of us is different. Everybody has a different comfort level with these kinds of things. And I am understanding that most of us view these as very difficult integrals. Yeah. Y minus 9. The derivative of sine is cosine. Derivative of cosine is minus sine. Does that make sense? You got that backwards in your notes? Yeah. Check that. Remember, the question was about this dx. Do not forget the derivative of sine is cosine, and then the derivative of cosine is negative sine. So if you think about it, in this particular problem, you could use x equals 9 cosine. That would work. The reason most people would choose x to be 9 sine, though, is because when you use the cosine, then you introduce a negative when you take the derivative. So it's got to be very careful about that. I know it's so unfortunate because it's like there's so much to learn, right? As soon as you think you figured it out, it's just overwhelming. And for that, I have empathy for you, right? Empathy means, what does empathy mean? It means I know how you feel because I've been there before, right? I think that's what it means. And sympathy means I just feel bad for you, even though I never sucked at this because I was always a genius. No, I'm just kidding. I sucked at this at one point too. I promise you I did. Okay, that being said, let's plug and chug, is my old high school math teacher used to like to say. So here's what the integral becomes. We start with x to the 4th downstairs, and then 81 minus x squared, and then upstairs is a 1. And so this integral becomes, the x to the 4th becomes 9 to the 4th. I don't know what that number is. I'll just write it as 9 to the 4th sine to the 4th theta. And then inside is 81 minus 81 sine squared theta. And then since I'm out of space, I'm going to write the differential up here, which was 9 cosine theta. And then I'll put my d theta here. So that's what happens when you perform the substitution. Now, as I said, when you do this first step, for most of us, it looks like we made an ugly thing much more difficult and ugly. And for that, I'm sorry, but it's only because we're only looking at it through the wrong sort of lens. Using what we know about algebra and arithmetic and some trigonometry, I have out front, I'm going to pull my 1/9 cubed out. And then downstairs, I still have a sine to the 4th. But inside the radical, what I'm left with is 81 times the cosine squared of theta. And then I have a cosine upstairs d theta. Now, what this ends up simplifying to is 1/9 to the 4th, because I have an 81 square root becomes 9. The cosines sort of, I don't want to say sort of, they cancel out. Now, we do have this one technicality here, which I pointed out before. And that is, and I told you not to worry about it in these calculations because, yeah. What? No, it's x to the power 4. You looking at h? Yeah. It's x to the power 4. So on problem H, it's definitely x to the 4th. I'm looking at it right now. You might have to zoom in. Let me see. Let's double check. So I'll come up here and look at it. Homework assignments. Homework set 4. Number H. Yes, it's x to the power 4. Make sure you see that. Power 4. Yikes, which makes this problem a pain, right? We think, at least. This is probably where you got stuck, I'm guessing. Yeah. You didn't get all your dreams answered by just going to Google and say, how do I integrate 1/sine of the 4th? I'm just kidding. All right. So does that make sense, though? So you're on the same page now? Yeah, okay. So it is the original problem. The question in class was, is this a power 2 or power 4 to begin with? It is a power 4. Now, here's what's interesting. Again, we're taking some leniency here. We're assuming that the cosine, we're only dealing with positive angles here. So this thing cancels out. So if you want to nitpick about this, is the square root of cosine squared actually cosine? Well, as I said, we're not nitpicking right here. It is. Fair? So as I alluded to the other day, unless otherwise stated, we're just assuming the angles between 0 and pi/2. Then there's no issues. Sine and cosine are both positive there. Some of you are like, I don't know what he's talking about, and that's fine too. It doesn't matter. But for those of you who want to nitpick about technicalities. Okay, look, so here we are. We're kind of at in a tough place because this is an integral we sort of, maybe we have seen, maybe we haven't seen. How do we go about handling it? What are we supposed to do? You can write this integral in a few ways. You might want to write it as cosecant to the power 4. You might want to write it as sine to the -4. You might say, well, how can I, what I've been doing? And my favorite thing you'll do is you'll say, we never did an example like this, O'Grady, so how am I supposed to know? And to that, I will come with the rebuttal. If I did every single example that you guys were required to know how to do, we wouldn't have ever got out of chapter 1 in the textbook. And right now we're supposed to be in like chapter 9 or something like that, 8 or 9, I think. So seriously, this is, and I'm only kidding slightly, so don't get like sort of, you know, overwhelmed. This is a difficult problem. And so the question we're at is, how do we integrate? You could say 1/sine to the power 4, or you could say, as I said, cosecant to the 4th, or sine to the negative power 4. I don't know how you sort of want to do it. either way, there's going to be, we think, at least we hope, a way of getting the answer if we're careful. It's worth noting again, something that I said probably 3 or 4 classes ago. What's probably the most sort of, I don't want to say overwhelming, but sort of like the worst thing about these integrals that require trig substitution is usually once we perform our trig substitution correctly, we end up with another integral that is not exactly a trivial integral. And that's just the nature of these things. So I don't know if that makes you feel better or worse. Did you try anything with this? Like what did you do? I'm assuming you went and looked it up and got sort of nowhere. Right. Okay, right. And then maybe you have some sort of identity with cosecant that can help you. Yeah.
When I use the square, right? I go to 1 over sine squared, right? And I go to 1 over cos squared and tan squared.
So you mean you want to break the sine of the fourth into sine squared squared?
Yeah, and then I did like.
And then you did one of them use the trig identity. So that's one way of going about it. Yeah. So 2 options that were sort of given by those in attendance today is rewrite it as a cosecant and maybe see if there's an identity of cosecant that's useful. And then I think the other one was to use the strategy we said before, try to rewrite this sine using some trig identities. I mean, those are both equivalent, whether you write it as cosecant or sine. You might also think, and again, I'm not suggesting that one way is better than another way. I mentioned to you guys on Friday that me personally, I like to keep things in terms of sines and cosines just because I feel like I'm more familiar with their identities than I am with using secants and cosecants. Now, that doesn't mean it's wrong to do that. It just means that's sort of how I like to do it. So, you know, again, this is one of those integrals where, you know, what you do is you come to it and you're like, oh, man, where do I even go from here? Should I even, you know, at this point, it's like you could be mad. You could say, well, Grady, shouldn't you have asked us to figure this kind of creature out, you know, knowing that it was going to come down to this? And then another thing to ponder is what if you use the strategy that I had mentioned before about sort of using, anytime you see an even power, use like those double angle formulas. Does that get you anywhere? Were you able to get this answer? Correct?
I got for the x squared.
Wow, well, this is x to the 4th, though. I mean, if that's a square down there, it's a slightly different problem, but this power 4 is really sort of a pain in the you-know-what. Does anybody have any thoughts? Did you what happened when you tried your identity? You get nowhere? Yeah. I like that. I got nowhere. It's okay to wave the white flag once in a while. There's nothing wrong with that. So let's say, since you asked the question, we'll go with your strategy, not your strategy necessarily, but we'll use the cosecant. One thing that's often, you know, it's just maybe goes against with what I said to you guys about I like to use sines and cosines is oftentimes when we ignore the cosecant, we might miss out on some very simple integrals that we're not familiar with, or because we have a derivative identity we might not recall. Yeah.
Can you also solve using the trig identities?
Using the what?
Using the identities.
What identities?
The trig identities.
Well, yeah, you're going to have to absolutely, once you get to this point, 1 over sine of the 4th, you absolutely have to use a trig identity. The question is, which ones will get the job done and which ones won't? and that's sort of the point I'm trying to make right now is that you can go different ways. So I guess maybe a better way of saying this is right now we're debating. So we'll go with we'll just, before we go any further, let's just rewrite this sort of in the form that was suggested. And that is, we recognize that 1 over sine of the fourth can be written as the cosecant to the power 4 of theta. So let's pause for a moment and think about how we might integrate this creature. It's sort of we're sort of what we're getting at. And again, this is, you know, these things are by no means elementary unless you spend hours a day integrating, which of course most of us aren't going to do. Now, what will typically happen when you do this, if you went to like Wolfram or one of those websites, they would probably tell you to use what's called a reduction formula, which we talked about last week. And again, there's nothing wrong with that. But what we want to say is there a way that we can maybe understand why that formula is indeed true?
May I tell something?
What's that?
So we can tell like cotangent square plus 1 is equal, let's say 1 over sine square x. So can we go through this formula?
Oh, wait, look, I mean, I think what you said is slightly incorrect, but in general, you have the right idea. We need to take this cosecant to the fourth and to break it into something that we have information on.
Like we can just type it down as like 1 over sine square x times minus 1 over like sine square x plus times minus 1. So we can write down.
Might work, but then that ends up, so the question, or what Zafalker is suggesting is maybe trying to break up the denominator.
Yep.
Now, that could work, and I'm not suggesting that
I have solved this problem, but with that, you know.
Yeah, but the thing with that is then you end up having to likely go to partial fractions.
Mm-hmm.
And I'm not, that there's nothing wrong with going that way. But what I'm suggesting is maybe we can get the job done slightly quicker if we take advantage of some trig identities. Is sort of the way I'm thinking about it. And again, I'm not saying that what I'm doing is right and what you're suggesting is wrong. What I am suggesting, though, is perhaps if we're going, if we're starting from sort of our limited knowledge is just say we're students in Calc 2, how can we sort of do it from what we would say sort of following our nose or brute force without relying on some fancy method? With what we'd rather do is we'd rather rely on sort of just going in an intuitive way. So let me reiterate what I mean by that. My guess is, and I haven't done this in a while, but my guess is if I went and typed this integral in the bottom one, cosecant 4, or 1 over sine 4, my guess is that if I went to Wolfram or Mathway or Simba, one of those web pages that does integrals, I would bet every dollar I own that they all tell you to use a reduction formula. So there's some little formula they give you to integrate powers of cosecant. And that's not wrong, but what I told you guys last week is, in my opinion, when you're trying to learn elementary calculus, and let's not get it twisted, that's what we're trying to learn. This isn't rocket science, this isn't quantum physics, we're doing elementary calculus right now. And when you're trying to learn elementary calculus, I think it's a bad idea to try to memorize or understand these big abstract formulas, because for me at least, they really hide what it is you're trying to learn. And so what I would encourage that you do is you do things like, okay, what do we know about cosecants? How do we integrate powers of cosecant? Do we have identities of the cosecant? For example, you know, it was already pointed out, well, what about our identities? And when most people say trig identities, I assume you mean the basic you know, what we call Pythagorean identities, and that is sine squared plus cosine squared equals 1. And why do I say that we usually mean that one? Because all the other ones are just derivations of that. They're all just equivalent ways of writing it. So if you start with sine squared plus cosine squared equals 1, then you can write that in terms of cosecants and cotangents. You can write it, as we've already seen numerous times, you can write it in terms of tangents and secants. And so one of the nice things to keep in mind is, you know what, for example, you know the integral of secant squared. What is the integral of secant squared? It's tangent. Why is that the case? Because the derivative of tangent is secant squared. And then you might ask yourself, is there similar things that I can gain from the cosecant and the secant? And of course, here's where you end up getting yourself, I don't want to say in trouble because that's a bad way, but what probably happens, and maybe this is what happened to some of you, is you feel like you're going in circles. Because you try one thing and then it doesn't get you somewhere right away. And then you say, okay, well, maybe this method was wrong. Let me try something else. When in reality, it wasn't maybe that the method you chose was wrong. It's just that you chose a method and you didn't sort of choose that method from the right perspective. And part of becoming a better problem solver, and part of the reason I think practicing integration is a useful thing to do, is because it teaches you, if you practice it correctly, it teaches you that some things when viewed in this perspective can be done. But if you have a similar problem and you view it in the same perspective, it gets you nowhere. However, if you slightly change your perspective, and I always go back to that thing, you know, if I look at this cylinder from one perspective far away, it's a rectangle. If I look at it from another perspective far away, it's a circle. You know, if I look down on top of it. Just like if I had a basketball. From far away, a basketball perspective, it's nothing more than a circle. So what I'm saying is oftentimes we sort of, and it's not our fault, I don't think, it's sort of the way that, how do we try to learn? So much of our schooling has been us in school, and we've been so beaten down with, you have to do well, you have to know these things, so we memorize things, and we memorize procedures. And what is one of the most common things I hear from students is, well, how do we do this one? Or, well, we didn't do this example, like I was talking about earlier. And the thing is one of the skills you want to have is you want to be able to adapt different techniques and themes to new problems. And so that's what makes this type of problem and integration in general so challenging, is that you can't necessarily follow the same script for every problem. You just can't. And what works on one problem is not necessarily going to work on another. So, you know, what I mean, you know, Shobit, you suggested using, you know, sort of multiplying it out type thing. Well, that strategy that worked for sine squared or for cosine squared, it might not work for cosecant to the fourth. And so then we sometimes have to say, okay, so what can I do then? Or how many things do I have to try before I give up? So, for example, you might say, okay, I know cosecant squared is 1 plus the cotangent squared. You might not know that identity, but it's a common identity. It's the Pythagorean identity. And if I just go and plug that in, does it do anything for me? So let's reset this problem in a sense that what we really need to know now is, how do we integrate cosecant to the fourth power? So the first thing I'm saying is that from a basic identity standpoint, I ask myself this: instead of writing this as cosecant to the fourth theta d theta, I'm going to write it as, using the trig identity, that cosecant squared is 1 plus cotangent. I'm going to ask, will this work? Now I'm asking myself this. I don't even know if it will. I'm trying to think of this problem pretending I'm in your shoes right now. So will this work? Because the first thing I say to myself is I'm going to say, self, what do you know about cosecant? What elementary identities do you have with them? And right away, that's the only one I can think of. So then I say, okay, if I multiply this out, will this work? But then it might seem like I'm in a similar predicament, because if I couldn't integrate cosecant to the fourth, if I multiply this guy out, I'm going to have to integrate cotangent to the fourth, right? And then I might not understand exactly how I want to handle that. So this is sort of where we're at. And what we have to do is we have to sort of figure out our way. How do we go about doing it? Do we go to the internet? Do we go look at videos? I guess you can always say, I'm just going to go and use whatever. Even if you don't understand it, you can say, I'm just going to use this formula, the reduction formula, which is not wrong. But the way I like to think about it is, can I actually do something that is, as I said before, following sort of my nose? So here's the way I'm going to think about it. And again, I'm not saying that this is the only way it is to do it, but this is sort of how I would do it, I believe, if I were a student. And this is how I would encourage you to think about it. I always like to say, follow your nose. So if I say this maybe works, but I want to try something else. So instead, I'm going to try the cosecant squared theta times cosecant squared theta. And then I'm going to apply this identity. So I didn't want to use this Pythagorean identity here, because then I would, if I used it on this whole term, I'm going to get another power of 4. And I'm trying to avoid large powers because I feel like I'm not getting anywhere with that. So my strategy is then going to be try to avoid that. So, okay, so if I go about trying to avoid that, then I can do, I keep writing on the wrong pad. I'm going to replace this second cosecant squared with this. So does anybody have a question at this point? Okay, so then the question would be, okay, what do I do with this? Well, I don't know. So let me just, as I said a couple times now, follow my nose. What would I do if I have a product? Well, why don't I break this into two integrals? And of course, okay, will that do me any good? Well, what do I mean by two integrals? Well, if I distribute this cosecant squared, I'm left with the integral of cosecant squared plus the well, I guess I should put my d theta in here. So I'm going to distribute this cosecant squared, and when I do that, I'm left with this. And before I go any further, you know, what I'm thinking about, part of what my brain is thinking right now is it's thinking, okay, O'Grady, do I know, is the integral of cosecant squared, is it easy? You might say, well, I don't remember that. Well, maybe sometimes we don't think about the integral of cosecant squared. But we do know the integral of secant squared is an easy integral because it's a derivative of something. Is the cosecant squared the derivative of something? So these are some of the little things that we don't quite always think about when we're in a calculus class. Like we memorize certain things because we see them all the time. Like we memorize the integral of sine and we memorize the integral of cosine. But very rarely do we memorize things like, let me zoom out of here. What is the integral? I don't want to use this page. What is the integral of cosecant squared? Or another way of saying that same question is, what is the derivative of the cotangent? And without much search or without, much fanfare, what we failed to see this whole time is that there was a simple identity that we could have used from the very beginning. And this is not on you, this is a similar thing for me. I don't have memorized in my head the derivative of the cotangent. I just don't. But I know how to readily get it. And I also know from experience that when I see cosecants and secants integrals, I know that one of the first things I should check is one a simple identity? So I hope you understand what I'm saying. I'm not saying I have all these things memorized in my head. I'm saying that I know certain times when to guess that something's simple. Now, let's pause for a moment because this is something that I know when you're a student you get worried about. Would I give you this particular problem on, say, an exam? And the answer is maybe not this level of difficulty, especially if you've never seen something like where we talked about this before. But now that we're going through this together, to me, on a take-home exam, this is a fair question. Because it's not an obvious one, and it requires that you do you have some background knowledge. This would be completely unfair if this were an in-class problem. I would never ask you to know this problem in 10 minutes. Do you think that would be fair? No, I don't. Ding, ding, ding. Anybody cool?
Here's my sister.
Oh my God. Well, does that mean no or yes? I'm just kidding. No. That was good. So you guys are missing out. We have phone calls in here. Okay, so let me reiterate this point once again. So I'm going to go back. I'm going to go back to the page. Here's my thought process, and I'm not even making some of this up. This problem was not obvious to me. It took me about 30 seconds before I remembered how to do this. And I don't mean I remembered how to do it like I had this problem memorized. What I mean by that is it took me a moment to sort of think about what are my options? What do I know from past experience that can possibly work here? And I literally wrote the first two things down that came to my mind. The first thing was, why don't I try the most obvious identity? Now, the most obvious identity to me, maybe not to you guys. And in fact, there's very few identities that are obvious to you. But one of the things I've been trying to get in your brain the last at least 2 or 3 classes is sine squared plus cosine squared equals 1 can be written in 2 ways. It can also be written in terms of secants and tangents. We've used that before. But it can also be written in terms of cotangents and cosecants. And that's what I'm using now. So again, I don't expect that you have that memorized. In fact, I technically only have the 1 memorized. I derive the other 2 when I need them, either in my head or on paper. What do I mean by I derive them? I know sine squared plus cosine squared equals 1. So if I want to know the other ones, guess what I do? I divide each piece by something. If I divide each piece by cosine, I get sine squared over cosine squared plus cosine squared over cosine squared equals 1 over cosine squared. And so then I know right away that tangent squared plus 1 is secant squared. So I don't memorize. I ain't wasting all that space in my brain. What my brain is reserving is it's reserving the familiarity of how to recall these other things. Do you get that? Same with integrals. The way I like to think about my brain is it's like file compression. I ain't wasting all the damn space up there memorizing formulas. What I use my brain for is to remember themes so that I can deduce and derive things quicker than I can without having to look them up. Now, I'm not being a perp here. I don't memorize everything in this class. There are many integrals that even I could expect you to do that I might have to take a few minutes to remember how to do them. But I'm not lying to you. I'm not going to pretend that I knew how to do this integral in a second, but I'm also not going to pretend it only took me a few moments to remember how to integrate it. And it's not because I remember doing this problem a month ago or 5 months ago or 2 years ago. It's because I remember certain themes. And it's not just integration themes. That's part of it. But it's also themes about problem solving. It's also themes about trig identities. Now, of course, my brain is going to process those things much quicker than yours because I've been doing it for a long time. I've experienced. I've been teaching calculus, and I've been doing advanced math longer than most of you have been alive. And I don't expect you to get these tricks as quickly as I will. But what I can do, if I'm going to help you at all, is I can at least show you that there's a process to doing this. So what is the process? Let me reiterate it again. I come back here. I do the obvious thing. And I hope in Calc 2 that what I did in this blue ink on the first page is obvious. I hope it is at this point, especially since we spent the last week doing it. Well, maybe obvious is a bad word. But once you see it, you're like, oh, I should have did it that way. Now, what's not obvious at all, unless you're one of these weirdo nerds who just integrates for hours a day. If you're that person, then it's obvious. But once you get to the bottom here, sine to the fourth, or excuse me, or 1 over sine to the fourth, or cosecant to the fourth, these are sort of random integrals. Very few people know how to do these automatically, right? And as you can see, they're so random that the software is programmed to use built-in formulas to do them. They don't even want you to think about how to do them. But I say you should at least once or twice in your life suffer through this, even if it takes you, what is it taking us now, 40 minutes? This is awesome, isn't it? And you were mad you couldn't figure it out on your own. We kid. Yeah, you should never get down on yourself with integrals. They're a pain. Okay, now, once I get to this cosecant to the fourth, in my brain, and maybe on my scratch paper, I go through my regular sort of checklist of what am I going to do. Is it obvious? Hell friggin' no, right? And then I see even powers. Then I start thinking, can I break it up? And I think that's going to be the way. Then the question becomes, how do I break it up? And so when I get here, I say the first thing I'm going to do is maybe I'll use the identity right away. But when I do that, then I realize I'm going to get this expanded thing that's going to have a power 4 in it. That seems like probably not the way. So then I back up a little bit and I say, okay, what if I only use that identity on one of the squares and leave the other alone? And then as soon as I do that, it dawns on me, oh crap, O'Grady, you should have remembered that the integral of cosecant squared is negative the cotangent. Does anybody have a question? Now, I'm not pretending that this is something that most people would have gotten in any reasonable amount of time. Let's not pretend that it is. But if I could only pause for one more second to remind you that what's beautiful about this supposed strategy is I've now seen it screaming at me. Because not only does me remembering that the integral of cosecant squared, what it is, by doing that, I've also solved the second integral because it's the same freaking thing. What is the derivative of cotangent? The derivative of cotangent is negative the cosecant. You don't have that memorized, at least I doubt you do. I technically don't have it memorized. I looked it up. Actually, I shouldn't say I looked it up. In my head, I had to remember it, but I would have looked it up if I wasn't teaching right now. I would have literally went to, the first thing I would have done is I'd say, I think it's this, and I'll double check. And it would have been. And so let me reiterate what I mean. I now know how to do these two integrals right here. And so before I do that, let me rewrite this down here. What I'm going to do is I'm going to switch these two creatures. Instead of writing it this way, I'm going to actually do it like this. So this is cosecant squared times cotangent squared. Watch how I write this. I'm going to write it in a cute way just because it's going to be more useful for me. I am going to write it as the cotangent theta squared times the cosecant squared theta. Now, the reason I'm writing it, it's the same thing I just did. I just erased it and wrote it in a different order. And the reason I'm writing it like this is because the derivative of cotangent is negative the cosecant squared. So if I go back to that page that I had to verify, even for myself, I am verifying, this is what I want to use, this thing right here, the derivative, maybe that's a, can I get a prettier, let me go to an image. What I want to use is I want to use this fact right here. Oh my God, what happened? Wait, Tom. I'm using this fact twice. The derivative of cotangent is negative cosecant. So technically I can yell at you guys and say, see, if you remembered this from Calc 1, this problem would have been easy. But no one remembers this, right? We always memorize the left-hand side. No one really ever memorizes the right hand. Well, I shouldn't say that. We memorize the first four. We ignore the last two typically. Okay, anyhow, back to the problem. What does this mean? Well, this means the first integral is obvious, and it means the second integral is a U substitution. So I'm going to write this down on the next page, step by step. This is negative the cotangent of theta, and then it's going to be plus this integral. I'm not going to touch the second integral yet. What a time to be alive. Okay, now I'm going to use a substitution. I'm going to say, I'm going to let y equal the cotangent, and then dy d theta is negative the cosecant squared d theta. So this is the substitution I'm going to use. Oh my God, we have a party next door. And what does this integral become? Well, when I do the substitution, it's going to be minus the integral of y squared dy. Wow, what a brutal, brutal integral. And so this becomes negative the cotangent theta minus 1/3 y to the power 3 plus c. Yikes. And we plug that back in. What a mean, mean problem this is. And we ain't done yet though, right? Because now we didn't write it in terms. We got to write this thing back in terms of x. Do you want your head to explode? I don't know. We got to finish it though, right? We got to see if it matches with Wolfram. We got to know. Who do you think would make the mistake, me or Wolfram? I'm guessing me. All right, so this is, I think this is very, I don't have a problem with us doing this because this is a hard integral. And it's a good example of us showing you that things are not always obvious, and they're not, even if they're difficult, they're not always direct. Oftentimes we try things that don't work. Oftentimes we try many things and we never get anywhere. That's problem solving. So you guys might not enjoy this as much as I enjoy this kind of stuff, but it's in fact problem solving. So we got to finish this problem. Let's see who's chopping up on the ones and twos. Yeah, that's exactly right, Zafalgar. This is a good problem. It's such a good problem. Now, in order to finish, we got to get these thetas in terms of x's. So let's draw our triangle. I'll come down here. Draw our triangles. And so here's our theta. And let's remember what we got to, I even forget what our original substitution was. 7 years ago, 9 sine of theta. That was our original substitution. So we know that x equals 9 sine of theta. So that means this has to be x and this has to be 9. And of course, as we would, the Pythagorean theorem tells us this is 81 minus x squared. So what's the cotangent of this particular angle? The cotangent of this angle is 1 over the tangent. So the tangent is opposite over hypotenuse. So the cotangent would be that inverted. So I think, as long as I don't make any errors, this would be the square root of 81 minus x squared all over x minus 1/3 times this thing cubed. Holy moly. I mean, that is an absolute fiasco. We can check it though. If we differentiate that, we better get what we started with before. Wow, that was brutal. Let's do 2 things before we go anywhere. Let's verify 2 things that we did correct. I'm interested to see. Maybe we made an error. So what I'd like to do is verify my cosecant business first. So what I'm going to do is I'm going to go to Wolfram, and I'm going to ask Wolfram to integrate cosecant to the 4th, because that's what we were doing, right? That was the big one in the middle. And let's see. As I predicted, indeed, let's see what they say step by step. Of course, use the reduction. I knew it. What did I tell you? They weren't going to do it the fun way. They do it the shortcut way. All right, but anyhow, let's look at their integral. They got -1/3 cotangent. They got something slightly different than what we got, but is it the same? And the answer is yes. It's just they've written it differently. So why is what they got the same that we got? The -1/3 cotangent. So let's see if we can. Oh, so Ethan, you want to know? You can learn it now if you want. It's not hard. You just use integration by parts, or you can just derive it. As I said, it's just not worth our time to learn it right now. I don't think it is, at least. But you're allowed to use it if you want, Ethan. If this were a problem on a test and you want to use a reduction formula, please do. Unless I explicitly tell you not to. Does that make sense? All right, so real quick, let's just make sure we got the same thing that these knuckleheads got. We got cotangent theta. They have a 2 floating around. Why don't we have a 2? Did we make an error? Or is that 2 immaterial? Also, they have a cosecant squared in their answer, but that shouldn't shock us because I'm just double checking it's correct. It is. That would have been bad if it wasn't. But no, it is correct. And the difference between theirs and ours is if we factor out a cotangent and we use the identity to put it back into a cosecant, that's what Wolfram's doing. So what Wolfram is doing, if you're keeping score at home, Wolfram is doing the following. I'll write it up here. So if I take my answer and I factor out a minus cotangent, so if I factor out a minus cotangent, what I'm left with is 1 plus 1/3 cotangent squared. I'll ignore the plus c for now. And then I'm going to replace cotangent squared with that identity that we had. What was our cotangent squared? Well, remember, cotangent squared, the identity we used from the previous page is we could write that as cotangent squared would be cosecant squared minus 1. Or excuse me. Did I write this down? Am I missing a minus sign? No. It should be fine. So let me remind myself. Cotangent squared would be cosecant squared minus 1. Okay, good. And then let's erase this y equals cosine business for now. So we got to make sure we're on the same page as the experts. So if I do some arithmetic, this becomes 1 minus 1/3. What's 1 minus 1/3? That's 2/3, correct? So I get 2/3 plus 1/3 cosecant squared theta. And if I factor out a 1/3, I get 1/3 with a minus sign, cotangent theta, and I'm left with 2 plus cosecant squared theta, which I do believe is what Wolfram had. We better double check before you fire me. Everybody ready? Let's get a drum roll. Is this what Wolfram had? Minus 1/3 cotangent times the quantity 2 plus cosecant. Dun, 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 dun. Oh, thank God. Oh, yes. Whew. I would have had a fire myself. Just to remind you, I'll minimize this creature. Oh, no. Why would it do that, you jerk? Why would it cover up the left side? This is the same thing Wolfram has, I promise you. He's negative 1/3 times the cotangent times the quantity 2 plus cosecant squared. This is exactly what Wolfram had. Oh, maybe if we minimize it this way. No, you jerks. Anyhow, I feel confident. Very good. All right, so now we go back here. Voila. And this is the ugly answer. So we're feeling good about ourselves. 55 minutes later. Okay, so look, I know I've sort of said this already, and if you have a question, please ask. Don't hesitate. But there are some comments that need to be said about this. This integral was challenging. Number one. Number two, it is possible that someone else has a more efficient method to compute this integral. And I don't just mean using the reduction formula. I mean, maybe you had a more creative way of going about it. There's nothing wrong with that if that's the case. Do not get overwhelmed or upset if you can't get this. This is not an easy integral. So if you think about it, it took us as a group almost an hour to do this. It would have probably taken me 10 minutes myself. That's a long time for something. And that means if you were trying to do this on your own, if you even get it, it's going to take you well over an hour if you figured it out on your own. And let's be honest, most of us don't figure this out on our own. Most of us need someone to give us guidance or watch a video on YouTube or, you know, get help from a tutor. This is not the kind of integral that is just you follow the rules and it works. It took a lot more work. That being said, it's worth once in a while to suffer through things like this. So, you know, don't let it drive you nuts. Okay, does anybody have a comment or a question? Now you're just praying I don't put that on a test. Or maybe I will. That could be your whole midterm in a couple weeks. Well, first off, you're going to have plenty of time to do the test. It's a take-home test. It's not going to be timed. Well, I mean, it's going to be timed, but not in a normal sense. You have at least many hours, if not more than a day to do it. It's a good problem. All right, any other questions about this homework while we're on it? Let's ignore that for a second. That was rough. What I'd like to do, though, I mean, I guess if you guys don't have any questions, let me point one thing out. Go back to what the hell? If you look at homework, if you look at problem 4 is the famous, let's find the length of the parabola problem. And if you want to answer problem 4, you need to know problem 3. Now, what I would encourage you to do, if you can't figure out problem 3 on your own, then just go get the formula from the back of your book or from the Wikipedia page, and you use that to answer problem 4. In fact, maybe we can do that briefly, and then we'll leave problem 3 for those of you who want to toil through it. And then we will be moving on to new heights next week, or excuse me, on Thursday. So let's do number 4. We already know what the length is. We've done it numerous times now. And so hopefully you guys can get this piece. And so the observation to make is, what do you need to do for your substitution? And it turns out that using our identities, what do we want? Well, we want to set x here. The correct thing is to set x equal 1/2 tangent of theta. And that means dx equals 1/2 secant squared theta. So that's the sort of the trig substitution that's going to get the job done here. And so when I do that inside, I get 1 plus 4 times 1/4 tangent squared. And then I get a secant squared. And then I also have a 1/2 out front. And then my bounds. What are my bounds? Well, if x is 0, then theta's got to be 0. And then here's one that's going to scare the ghost out of you. If x is 1, then theta has to be the inverse tangent of 2. So this upper bound becomes the arctan of 2, which is often scary for the youngins in calculus. But it is a number. The inverse tangent of 2 is a number. It's just that we don't have a rational form of it. It's irrational. So what does this become? This becomes 1/2 integral 0 to arctan 2. And then inside the square root, it just reduces to secant squared inside the square root. So what you end up with is secant cubed d theta. Now, we're going to not skip, but it's a bad way of saying it. The integral secant cubed is not one that most human mortals have memorized. In fact, I would doubt anybody has it memorized. Well, maybe some people do. I don't. And so what I'm going to do is I'm going to just use part 3 to tell me what it is. So it's 1/2, and then it's also going to be 1/2, and then this is secant theta, tan theta, plus the natural log of the absolute value of secant theta plus tan theta. What a beast. And then I have to evaluate this from 0 to the arctan of 2. What a beast. Now, there's a couple things it's useful to figure out before you start plugging these numbers in. So let's just look at some basic things. First off, what's the secant of 0? The secant of 0, not the secant of theta, the secant of 0 is 1. The tangent of 0 is 0. That's useful to know. Now, what would the tangent of the arctan of 2 be? Well, that's just 2. Think about it. That's like saying, what is the square root of 2 squared? Right? So the inverse 2 plugged into the actual function, it just cancels each other out. And so the only one that remains a little bit tricky is, what is the secant of, we also need this one. What is the secant of the arctan of 2? Well, you're going to need a triangle for this. So if you write down a triangle whose tangent is 2. So let's draw that. What's a triangle whose tangent is 2? The tangent is 2 would mean 2 over 1. And so that means that this is the square root of 3. Excuse me, square root of 5. So you should ponder this. Not literally do it, but you should. Why is this square root of 5? Because it's 4 plus 1 in square roots, so this is square root 5. So what is the secant of this angle? The secant is 1 over the cosine. So the secant is what? 1 over the cosine would just be, well, what's the cosine? The cosine is 1 over the square root of 5. So then the secant of that would be 1 over the square root of 5. If the cosine is 1 over the square root of 5, then the inverse of that would just be the square root of 5. So I know that we're not all experts in trigonometry, but you should get to the bottom of this. At least that's my advice. Okay, so when I do this, when I plug everything in, first off, I'm going to pull this 1/2 out. So this becomes 1/4. Now I'm going to plug in the arctan of 2. So the first thing I'm going to get is the square root of 5 times 2. Then I'm going to get plus the natural log, and then this is going to be the square root of 5 plus 2. And then when I plug in 0, what happens when I plug in 0? Well, the first term goes away, and then it's going to be log of 1 plus 0. Yikes. What a fiasco. But that just turns out to be 0 anyhow. So what you end up getting is 1/4 times the quantity 2 root 5 plus the natural log of 2 plus root 5. Holy heck. That is an ugly number, but it is the arc length of the parabola. So this is at this level, I would highly encourage that you spend some time thinking about this. We kind of went through it quickly, so there's a lot of details you might have to fill in. What you should do, though, is you should go and make sure that you got the answer correct somehow, some way. For example, if you go to Wolfram, what does Wolfram tell you? And Wolfram's going to spit it out differently, but they're going to give you the same thing as it. They're going to give you an equivalent form of this. So Wolfram will use what's called the hyperbolic sign. Let's double check. So we got 1/4 times the quantity 2 root 5 plus log of 2 plus root 5. Yikes. So if we go to Wolfram, they're going to get the same thing, but they're going to write it differently. See, now they use what's called the hyperbolic inverse sine. But you can write this in terms of logs and you get the same answer we got. By the way, a homework or two ago, we asked you to approximate this integral using Riemann sums. And if you did it correctly, you should have got something like this. So, by the way, this is a very important problem for a few reasons, application reasons, but also out of pure human endeavor. Humans have wondered for a very, very long time what the length of a curve is, particularly a parabola. And it took humans thousands of years to invent calculus before they can figure this out. Okay, anyhow, does anybody have a question about this? So look, this problem, and again, this is, I would argue that most problems on this homework are very difficult, and they're tough for you guys to not only be able to do on your own without making errors, but to also understand all the steps. So my advice for you is to really think about this problem, the arc length. It's a fascinating problem. Now you're going to say I don't care, but I think it's fascinating. Anyhow, now you can go paint, you know, the exact amount of paint to buy if you want to paint a line, or excuse me, a curve. If you want to paint a parabola's curve, you won't waste any paint. You go buy exactly this amount of paint. Of course, then you get into the interesting philosophical question, well, how wide is our line? Thickness. Believe it or not, there are applications of, as you would imagine, your standard applications of arc length. You know, like what is the distance that an object traverses through? You know, maybe a plane flying or space shuttle. Then there's ones you don't think about. Maybe in computer graphics, we need to know the lengths of curves. So I don't want to, I might say maybe as if that's not true, but that this is an application of computer graphics and stuff like that. So anyhow, there's lots we could talk about, but we don't have all day. You guys don't have all day. Of course, you know I could talk. Anyhow, listen, thank you guys. If you have questions, let me know. Otherwise, we'll see you on Thursday. So hopefully you pay some mind to this, and I will talk to you soon. If someone has a question, chat it up. All right. Thanks. See you too, Muhammad. Take care, everybody. Thank you very much. And I will see you guys when I see you guys. Thank you.